Hi friends, this is PH5502 Unit 4 Solid State Physics by Dr. M.R. Gadhvi. In case of a one dimension, we have seen that the normalized wave function in the shape like psi of n under root twice of a sine n pi x upon a. Whereas in the three dimensional case, the similarity between one dimensional and three dimensional is you can visualize the three-dimensional case like a three one-dimensional case, and therefore three-dimensional case is nothing but the product of three one-dimensional normalized wave function, and henceforth the equation is come across with the under root of 2 by a, under root of 2 by b, and under root of 2 by c for all the three dimensions. That become under root 8 by abc sine nx pi x upon a, similarly ny pi y upon b, and nz pi z upon c, where nx, ny and nz in mathematically you can say it's integers, but otherwise in terms of physics we can understand it's a principal quantum number. So ultimately they will gives us the idea about the energy associated to that. If you find it out the eigenvalue of the functions, then it would be h square upon 8m nx square upon a square plus ny square upon b square plus nz square upon c square. So these two relations are the case of a three-dimensional case. But if we restrict our case for the cubic structure where a, b and c the lattice parameter are constant, then the relations or three-dimensional wave function become 8 upon a cube and sine nx pi x upon a, sine ny pi y upon b, sine nz pi z upon c. Let us take one example to understand the concept of a degenerate or degeneracy. So we are choosing the principal quantum number like nx is equal to 1, ny is equal to 1 and nz is equal to 2. The same thing we can reshuffle and we can make it nx is equal to 2, ny is equal to 1 and nz is equal to 1. Similarly, the third possibility is nx is equal to 1, ny is equal to 2 and nz is equal to 1, and correspondingly there are three wave functions I am able to get. And you can look at here, in all the three cases the normalized constant is remain common, and therefore I am replacing with the a just to make it ease of the mathematics. Under root of 8 upon a cube because a is equal to b is equal to c, that is a cubic structure. But if you look at here, this is a nx pi where n is equal to 1, so it is a 1 pi x, this is 1 pi y, and this is nz pi z, and that nz is equal to 2. The associated eigenfunction that is given by this, the eigenvalue of the function that is given by n square plus ny. Now since there is a cubic structure, so this is denominator is common, that is a square, so a square I am taking out, and in that case my eigenvalue of a given function or the energy value is exactly similar to 6h square upon 8m square. Now what is exactly the degenerate? Degenerate means when you have a several states but they have the same energy, that is called the degenerate. Like over here you have three combinations 2 1 1, 1 2 1 and 1 1 2, and in all the three having the energy same, and therefore it is referred as a triply degenerate or a threefold degenerate. This all the three states are basically independent states. the question arises, how we can say that independent? Because their quantum numbers are different. In one case it's a 112, second case it's a 211, third case it's a 121, and therefore they are independent. Now, by chance you have the quantum numbers identicals, that is nx, ny and nz quantum numbers are same, then that reshufflement or the combinations are not possible, and therefore they are referred as degenerate. That means they cannot have any kind of a fold. It's a simple non-degenerate case. Anyway, let's look at to the case of a degenerate case and how it is going to be resolved. Since you having the energy is a constant, but still I am inquisitive to check it out how exactly the different energy associated to each energy state. And to understand this, let me take some mathematical treatment to my set of equations. Let us increase size of my metal box or three-dimensional box by a very small amount, that is dA in a direction of x. Now if you look at your breadth and thickness is remain unaltered because I am just modifying the dA. Therefore if you look at this particular state where the x is double than your breadth and thickness, and therefore the energy associated to the first state, that would be 4h square upon 8m square, whereas the raised 2 state, that is 121 and 112, having the energy in the x direction, that would be h square. You can look at here, this is a 3 independent state, that is 211, 121 and 112. How I shall understand how I am able to resolve this 3 states? So I choose I understood that 211 having the energy associated in the x direction, that is 4h square upon 8m square. And to understand that, let me take a one box and let is their coordinates are x, y, z, and let me increase the very small element of the length in the direction of x. By doing so, I am not altering the rest 2 energy state, that is 121 and 112, because their energy is still h square upon 8m square. So here we having a very clear vision that if this is a particle box and if I am increasing its x direction with a small amount of dA, then the energy associated to the x, this will be decreases because a is in denominator, but over here the a is also decreases, but the amount of decrement will be little bit lesser. Let us check it in detail. So over here if you are looking, this is a very first step, so that is related to the 211. That energy is decreased by how much? So this is the original cubic box, and now I am increasing the box by dA, so the length is increased by the factor dA. So this is 8m square, this become a plus d whole raised to square, and then I am doing the mathematical variations and I am able to get the change in the energy when a dimensional box is increased by the component dA in x directions. So this relation is basically h square upon 8m square, 8 dA upon a, that is your change in the decrement of energy. Keep it this in your mind, and at the same time just try to understand, but the other two state where the energy is 1 in the x direction, energy over here also having a 1 in x direction, and therefore their energy will be decreased by the h square upon 8m square 2dA. How it is appeared? Let us calculate that as well. So if you look at this part and this part is similar. How it is increased? Because now it is only a 1 this is the without increment of the dA, and this is with increment of a dA, and then you are taking a difference of them, and if you expand this relation, finally you can having the h square upon 8 ms square. So this equation is the decrement of energy in case of the rest 2 energy state, and this is the decrement of the energy in the case of the first wave function, that is a 2 1 1. This is 1 2 1, this is 1 1 2, where this is the decrement in the case of 2 1 1. Let us try to look at on the graph. So on y-axis I am taking the energy, okay, as a unit of h square upon 8 ms square, 8 h square upon 8 ms square. So this is simply a multiplication of the n. Okay, so now here also a very interesting thing is given. 111 is basically a non-degenerate state. That means the energy is constant. Over here we have the case what we are discussing about, and that is a 6 h square upon 8 ms square. So on a 6 unit we having a 3 energy state having the same energy, and therefore they are said to be a degenerate because the energy is constant but having a 3 different states. To resolve them, we are incrementing the width of that one of the dimensions, and let us say I am increasing the width by dA in the x direction. So the x is a 2, I am increasing dA, and the energy decreases. How much it is decreases and how it is decreases, you have already knowing. This is a unit box and you are increasing in the x direction like a dA, and therefore the change in the energy, that is equivalent of h square upon 8 ms square this way. Whereas this 2 energy where the x component are in the one time, or it is half of this particular the dimensions what you are changing or in the first case. So the change in the energy in this state is larger compared to the rest 2, and therefore here you can look at, here they are lying on the same energy level, but here they are not lying on the same energy level. That means you are able to resolve this 211 energy level with respect to the other 2, and that way we are able to degenerate the energy levels of a degenerate or a double fold or a triple fold and so on. So in nutshell, what are the way of doing so? So you can also place the you have to increase the dimensions of the size, and that you can triggered by any particular external agency, like you are placing in a magnetic field, and when you are placing in a magnetic field their overall length will be enhanced, and therefore you can having the change in the energy state. I think Zeeman splitting is one of the good example or good analogy, correlate analogy over here. This is the change in the this is definitely less change compared to this one, because here it's a double than the x component over here numerically. Okay, so basically overall observation what we have seen that, or rather this was the observation done by the Sommerfeld, that the assumption of a classical statistics where you having a very number of the particle may have the identical energies because they are very close to each other, and in the case of this particular energy association they are referred as the almost continuous energy. If you look at here statistically, that electron gas where it is not exactly the analogy like a gas, a normal ideal gas where the molecule doesn't have any charge, but over here the electron gas where the electron or your candidate having a charge, and therefore you cannot use a normal Boltzmann statistics, but you should go with the fermion statistics because it's similar or resembles to fermions, and therefore a Fermi Dirac statistic should be involved over here. That is what a first correction made by Sommerfeld. And Fermi Dirac statistics is applied because the particles are indistinguishable. This is a tagline. Okay, so that's how we are able to do so. Since there are many number of electrons are available in the metal, some around in the order of 10 to the power 23 to 10 to the power 28 per meter cube. Let a piece of metal having a macroscopic size of 1 centimeter, then from that energy calculations, that is n square h square upon 8 ms square. On that basis, if you are considering their ground state energy, the lowest energy, where nx, ny and nz is equal to, you considered 1, then your order of energy is something about 10 to the power minus 15 electron volt, and hence you can consider to be as almost like a 0 for practical purposes, very less electron volt. There is no use of a practical approach, practical purpose. In addition to that, if you look at the macroscopic behavior size of the sample, then their spacing between the energy levels will be very less, hardly 10 to the power minus 6 electron volt. So that separation between two electronic states are not too high, and therefore they are said to be almost continuous, or rather you use the word band rather than the electronics individual energy level, or some specific way or more scientific way you should use the word quasi continuous. So if you look at them minutely, as we have seen by changing their length or so of your unit size of your unit cell, then you can definitely resolve them. That means they are not continuous, and therefore the word appeared, it's a quasi continuous. That means it is mimic as continuous but not actually the continuous one. And the energy you can calculate definitely with the help of this equations, right? And this is the Fermi Dirac distribution functions. So that is the Sommerfeld has suggested. So now the next topic discussion we will made on the basis of not the bosons distributions, but we will be discussion under the Fermi distributions. What is the Fermi Dirac distribution? Fermi Dirac distribution, so I think you had heard about the Fermi level, and Fermi level is a kind of, at absolute zero temperature, the all electronic states are filled up to a certain energy, and above that energy all the electronic states are empty. So the topmost filled energy level, I repeat, topmost filled energy level are referred as the Fermi energy level. So in a way, if you look at that, there is a stacks of so many energy level, and topmost filled energy level is a Fermi level. That means below to Fermi energy level, all below to the Fermi energy level, that means E is less than EF, then you are finding the probability of finding that particle, that is the electrons, indistinguishable particle, that is 100%. But when your energy is greater than EF, one does not know. So the possibility is finding get particle is 100% zero at absolute temperature. Don't forget the entire thing we are talking about at absolute zero or at absolute temperature, because as the temperature will increases, electron are getting external agencies or getting energy through external agencies, and therefore they are go to the higher excited state. In that case, this probability is not zero, because now the temperature is not zero. Okay, so this is the case f of E is equal to 0 where E is greater than EF, only true in case of absolute 0. Similarly, f of E is equal to 1 for the case of E less than EF, that is only true in the case of absolute 0. Anyway, we will look at to the next topic in the next lecture session. By the way, over here the author has given a few list of this one, like 211, 121 and 112. That is the unit energy 6, and it is a triply fold or a threefold degenerate. As well as he has given the idea about 111, 222, they are the non-degenerate state. But like 123 is a six-fold degenerate. Can you see here, six-fold? That means, to be honestly speaking, you have to make all permutation and computation permissible combinations. That will give you the total number is 6. If you look at 123, 312, then you are making 231, 132, 213 and 321. And another combinations, that is a 421, and over here it is again a six-fold. Just take care, I had recorrected over here because in the books there is a misprint. Now this is 421, here also it's a 421, it's a 142, here also it's a 142, so it's just repeating again. So ideally it become a 412 and 4124 and 241. Okay, so this all are the few cases, and I think I can pick up any one of the example of a threefold or the sixfold on a day of exam, and I can ask you is the either on the variations of y dimensions and how the energy will be resolved, or how the three fold degenerate states you can make it resolved, and what are the states to be changing. Anyway, so till this point I am stopping with this topic. Thank you so much for paying attention. Stay home, stay safe.